From start to finish, the project involved obtaining access to the actual voting machines and to the memory cartridges that they ship with. Taking those machines apart, understanding how they work from an electrical perspective, disassembling the software that was compiled into their read-only memory chips, finding a vulnerability in that software, developing a new return-oriented programming toolkit to take advantage of that vulnerability and allow the attacker to inject any code he wanted, any behavior that he wanted without injecting any code, and to build an actual full working exploit that steals votes. What was interesting is that all of this was done starting from just the actual machines themselves, without access to any vendor documentation, without access to any of the source code. It's a bit surprising that the overwhelming consensus in the computer science literature for how to run voting machines is minimize the use of computers. Really, it sounds, from what we know now and what we know how to do now, like the best approach is to use optical scan of the machines where voters actually vote effectively by filling out Scantron sheets, and then have those counted at the polling place to tell them what they voted and whether that was undervoted, overvoted, okay, right there, and then to have those optical scan ballots recounted and audited at election headquarters. That, if combined with electronic ballot markers, which are effectively voting machines that fill out a Scantron sheet for you, for example, if you're blind or otherwise disabled, can give many of the same advantages that direct recording electronic voting machines have, things like the square FEC advantage, while allowing a lot more auditability so that people can be convinced that the election really came out the way that the machines tell them that it came out. So this research really connects directly into UCSD's interest in voting policy and in technology policy generally, but it also ties into our work in system security. Return-oriented programming was not something that we developed for breaking voting machines. It was something that we developed initially for looking at the security of features that were introduced in Windows XP Service Pack 2. Return-oriented programming turns the program against itself, takes little snippets of code as part of that are already part of the program, and puts them together to synthesize something that's nothing like the program. In fact, to synthesize arbitrary, malicious behavior. The effect is something like picking a word or a phrase or a sentence out of a story to put together a completely different paragraph that means something completely different. And we originally showed that return-oriented programming is possible on desktop PCs running the x86 processor family. The inner workings of return-oriented programming depend on the processor architecture. Later, also here at UCSD, we extended it out to other processor families that are RISC processors like Sun's Spark chips. And other folks working elsewhere have also looked at PowerPC chips and some other embedded processors. And as part of this project, Steve Chekaway, my student, was able to extend return-oriented programming again to another processor architecture, the Z80, which is a funny 80s sort of design related to the x86, and to show that it's possible to build any program that you want out of the 16 kilobyte BIOS that's loaded at all times in the AVC Advantage voting machine.